Okay, so Mr. President, honorable professors and attendants, it's our pleasure to introduce this technical forum today on the trends in intelligent manufacturing and robotics, since KFUPM has created a dedicated research center on this area. And I understand today that we have an international audience, and it's my great pleasure on behalf of our team to introduce the president of KFUPM, Dr. Muhammad Al-Saggaf, for his address note. Please, Dr. Muhammad, the floor is yours.
Okay, thank you very much, Dr. Samir. Bismillah ar-Rahman ar-Rahim. Alhamdulillahi Rabbil Alameen. Wassalatu wassalamu ala ashraf al-anbiya wal mursaleen. Sayyidina Muhammadin wa ala alihi wa sahbihi ajma'een. Distinguished participants in this forum, also distinguished organizers, distinguished attendees and speakers, whether from KFUPM or from abroad, I'd like to welcome you to KFUPM and to another one of our meetings and symposia and workshops and forums. We are taking a very steady and fast journey of transformation at the university. As part of my address, I will very briefly touch on it and talk then about today's forum. KFUPM is interested in pushing the envelope of science and technology, in making sure that this science and this technology has an actual impact on humanity. Its objective behind research is to improve the human condition and to amplify impact on society, such that academia has a substantive and documented and clear impact on the livelihood of people around the globe. And whether that impact is easily measurable, such as tackling issues of water scarcity or hunger and so on, or it's a bit more sophisticated in the sense of better efficiency and manufacturing, more complicated setups that would reduce cost and allow humanity to achieve things at a lower cost and optimize resources and minimize waste and so on. So that is really the objective of our research at the high end. The university is focusing on many things. An important thing that it is focusing on is pushing the agenda of digital foundation, computing, and integrating these concepts in everything we do. Integrating it in research is a given, but also integrating it in academia as well. Over the past 2 years, we overhauled all of our academic programs, all of them, without an exception. And we built them on a platform we call the AI plus X platform, Artificial Intelligence plus X. So you first learn AI and related disciplines, and then you build your discipline on top of this. So if you are a petroleum engineer or in finance or a mechanical engineer or systems engineer, you first learn advanced Python, data science and big data, artificial intelligence and machine learning, business and entrepreneurship and career essentials and so on. And then you build your discipline on top of this, such that we graduate students who are ready for the future. We also recognize that future economies need to compress the cycle of academic training and produce output that is ready for deployment in the workplace. This is why we developed 40 new subspecialties called the undergraduate concentrations in future topics such as quantum computing and hydrogen mobility, cybersecurity, and so on. Process safety, and some of them are not so futuristic, but such that our graduates are ready to be effective members of the workforce as soon as they graduate. No need for training and a waste of time of developing a generic graduate into a specific job. And of course, holders of these concentrations are fully capable of and fully certified in the general topic as well. They just take a little bit more depth into a certain field. We also recognize that the people who are going to change the economies of the world are, and please don't get upset at this statement, are not the PhDs. To actually change the economy, you would be a professional, whether starting a new venture or participating in a company with substantially improved performance. The PhDs are going to change the future as a whole by inventing new things, but the direct application into the economy are done by the professionals. So we launched a suite of industry-linked master's degrees, in fact 35 such degrees over the past 2 years, and they have become very popular. This year, in fact, we are graduating over 500 such students, and who will be really taking a lot of burden in pushing forward the agenda of transformation in whatever economy they are, and in particular in the Saudi economy. And finally, we overhauled our research program. We ensured that every faculty member at KFUPM is jointly appointed in a research center. We launched a suite, in fact, 20 new research centers, either new or overhauled. One of them is led by Dr. Samir Mekid, which is the center organizing this forum on intelligent manufacturing and robotics. And all the other ones are like this. They are thematic. They are not disciplinary. So each center has 7, 8, 9, 10 different disciplines, from advanced materials to advanced communications to intelligent secure systems to mobility and logistics and so on and so forth. And so we are, and our goal is quadruple the annual research output of the university, and to make, as I said, a substantive impact on the application such that humanity is served well. Today's forum is one that is crucially important, because in the end, to make things, to make products, you need to manufacture them. And to the extent that you are able to do this effectively, efficiently, and with minimal waste, and with vast speed, and with a lot of flexibility in reconfiguring and so on, then you are able to really impact the economy and therefore the lives of people. And there are many things that you will be discussing, from smart manufacturing systems to the relevance to IR 4.0 to monitoring and machining and robotics and so on, disassembly and remanufacturing and so on. So it is a very important topic. I'm very glad that we have international presence in it, and this is our goal, is for KFUPM to be a hub for international discussion. I will not bore you with more talk. I wish you a very informative and useful and beneficial, and most importantly, an enjoyable forum, and that this gathering and meeting will be repeated many times with even more sophistication and more participation, and therefore more widespread benefit to the university and to society at large. Thank you very much.
Thank you very much, Dr. Saggaf, for this inspiring opening remarks, as usual. Now it's also my pleasure to introduce the Vice President for Research and Innovation, Dr. Ali Al-Sheikhi at KFUPM, for his introductory words. Please, Dr. Ali, the floor is yours.
Thank you very much, Dr. Samir. I'm really happy to be here with you. I'd like also to thank the President for his opening remarks. I think he said all the things about the academic and the research transformation and the transformation as a whole at KFUPM, which is very ambitious. And from the research sector, since I'm the Vice President of Research and Innovation, we focus, as the President mentioned, on the impactful research that is very beneficial to the human condition, whether here for Saudi Arabia or for the humanity in general. So let me just welcome all of you, and I'd like to thank you, Dr. Samir, thank the organizing team, Also, I'd like to thank the distinguished speakers today, Professors Zan from New Zealand, Sharif Ullah from Japan, Roberto from Italy, Pham from UK. I hope that I did not miss anybody for participating in this event, and also special thanks to the attendees. And I hope a very good morning and beneficial forum. I think that, as I mentioned, the president said it all. I just need to maybe fill a little bit of some gaps that also the university have established an excellent ecosystem that will push forward towards having things to be developed. So we have the innovation ecosystem is ready through the TAB, which is the Technology Advancement and Prototyping Center that has all the facility for manufacturing or doing the prototyping for testing and other things. We have also in a year or so, we will be finishing from our, we have also the Science Park that has over 18 companies, really big companies like Schlumberger, Halliburton, Baker Hughes, Yokogawa, and others that will help also in taking our science production in terms of papers and patent to the next level of the TRLs for possible licensing and commercialization. Also in a year or so, we are going, inshallah, to finish from our business park that will be also helping completing the cycle for our ecosystem. So we hope that KFUPM at the end will be an excellent place to work, live, and play as well. So this will complete the cycle, hopefully. Needless to say about this forum, which is about an important topic, trends in intelligence manufacturing and robotics, that this is really an important one because the world in general invests a lot in manufacturing. Saudi Arabia in particular has a growth of 7.5% every year in the manufacturing sector. And also the industry in Saudi Arabia is worth of around it's around $4 to $5 billion. So this is an important really forum that discusses the manufacturing process and trying to automate the manufacturing process using the additive manufacturing 3D and 4D, using the immersive technology like virtual reality, augmented reality, to improve the design, maybe the look and the feel. Try also to use the resources more carefully to really have more product that is environment friendly. So we hope that our manufacturing process at the end will be greener or even green totally, hopefully. So as I'm emphasizing the importance of this topic for the kingdom, for the humanity in general. So that's why we created this center actually, because we understand also the importance of manufacturing, which is the intelligence manufacturing and robotics, led by Dr. Samir Mekid. And also we have other supporting centers, not supporting, but we understand that really to produce something, a number of it's all of them are interdisciplinary, but a number of them should really work together to really produce something at the end. So we have also other centers that I'm sure that they can contribute also in the manufacturing, like the advanced material, energy storage, BVs and the power system, and all of those I think will add on to the digital manufacturing. And I don't want to talk more, but I really hope all the best for all of you and enjoyable and fruitful forum, I hope. And thank you very much. Assalamu alaikum.
Salam. Thank you, Dr. Ali, for this informative talk. We have today 4 presentations with a pause of 10 minutes in the middle. We'll allocate about 10 minutes questions and answers after each presentation. So the panel today is almost covering the whole world. We're starting from New Zealand in the Far East. That is night by now. And then we move against the time, okay, towards Japan and then Italy and UK by the end of the forum today. So the first presentation will be given by Professor Xun Xu on digital twin enabled smart manufacturing. Professor Xun Xu is a chair professor of manufacturing at the Department of Mechanical Engineering at the University of Auckland. He joined the department after completing his PhD from the University of Manchester. It was then UMIST. I joined when it was UMIST, by the way, in UK in 1996. He has been working in the field of intelligent manufacturing solutions for some 30 years. Dr. Xu is an internationally recognized expert in smart manufacturing systems, cloud-based manufacturing, and IoT-enabled manufacturing. He serves as an editor-in-chief, associate editor, and member of editorial board on a number of international journals, and has published over 350 research papers. He is the director of the Lab for Industry 4.0 Smart Manufacturing Systems, known as LISMS, the only lab for Industry 4.0 in New Zealand. His current research focus is around the I4.0 technology, including smart factories, digital twins, cloud manufacturing, augmented reality for manufacturing, and big industrial data and data analytics. He is a fellow of the ASME and Engineering New Zealand. In 2020, he was named among the top 20 most influential professors in smart manufacturing by the Society of Manufacturing Engineers, SME. And he was recognized by the Web of Science as the highly cited researcher in 2020. Without further delay, the floor is yours, Professor Xun. You are muted.
Right, okay. I'm just going to share my screen. I'm just trying to run this. I think you're seeing that. Are you seeing the right screen?
Yeah, that's fine.
Okay, that's the presentation window, is it?
Yes.
You're looking at? Okay, excellent. Right, okay, thank you, Dr. Samir. Good morning and good afternoon and good evening, depending on wherever you are. Well, we all know COVID has changed the entire world and COVID has changed the way we do things. Indeed, it has changed our way to do things because it made us a habit of virtually connecting with any people. And this is one example that I'm really privileged to give this talk. I just can't think pre-COVID this will happen. So we got into this kind of habit, which is perhaps the upside of COVID, if you like. If there is an upside of COVID, this will be one of them. So I thought I should perhaps start with a good news that we have just received, which is this paper. So we received this Best Paper Award from this Journal of Robotics and Computer Integrated Manufacturing. So it's a Q1 journal in the area. So what they do is I think 5 years ago, the journal established the Best Paper Awards. So every year they nominate a paper, depending on the citations in the past 4 years of that paper. So this paper titled Digital Twin Driven Smart Manufacturing, Connotation, reference model, applications, and research issues. So that a paper that has received the most citations in the past 4 years. So we're very pleased to receive the awards, and it's a collective effort from multiple people in the departments, but also in the faculty and people from other departments. So it's a paper that's a culmination of a long history of research in the area related to Industry 4, but more importantly, smart manufacturing. So, so what I'll do today is I hope I'll make use of the time I'm given, about 50 minutes, and to talk about Industry 4, but very briefly. I guess I can understand people here already have a good understanding about what Industry 4 is. And of course, I'll talk about smart manufacturing, but in particular, the terminologies such as cyber physical production systems, CPPS. And I'll move on to the topics related to digital twin. The first up is the state of research. So I'll try to give you an overview about the research in this area in terms of who is publishing the most cited papers, which journal publish more papers in the area, which conferences you can see more papers in this area. So a bit of that. So we've done some literature search around this area. Then I will talk about definitions of digital twin. I won't be going to debating about which definition is correct or not. So there isn't the right or wrong definition for digital twins, and depending on where you're coming from. So definitions can differ. I'll talk about applications and models and the twinning methods very briefly. When you say digital twin, so if you have a twin, that means you have two twins, and how do you communicate between the two twins, in the physical and the digital twins. I'll also talk about the international standard, which is just recently published. It's an ISO standard on digital twin for manufacturing. So it's a very important standard for manufacturers that are going to consider digital twin technologies for their business. Well, for researchers as well, I guess, it provided some fundamental definitions and concepts and framework for digital twin enabled manufacturing. So I'll talk about that. And you can easily Google online, and if you have a library that contains all the international standards, and you can find it already in the library. To finish off, I will have a few case studies or perhaps examples that we have worked on in our laboratory, some with industry partners, just to show how digital twins can be developed, what type of technologies that can be utilized, and the benefits you may get from implementing digital twin. So that's what I hope to get through today, and hope I can do so within the time that I'm allowed. Okay, so I'll start with Industry 4.0 as I promised. But perhaps only by showing this diagram, a diagram perhaps have been seen by millions of people around the world in the early days of Industry 4. You can see the way I spell Industry 4, which is the German way, of course. And so we all know it's a high-tech strategy from Germany, started in 2011. So I wouldn't go through all the industrial revolutions before the fourth industrial revolution. So this number 4 industrial revolution, you can see here, the key words are cyber-physical systems. So that will be the key leading point into my topic, which is digital twin. So we'll go from Industry 4 and then to cyber-physical systems, and then I'll go into digital twin concept. So it's a good segue into my talk today. I thought I should show this as well. Again, it's a diagram coming from German government documents. This is basically clearly showing the two parts of the cyber physical system. There's a physical system, and then there's a cyber part of the physical system. This is essentially what we're referring to as digital twin at the moment. So this is the digital twin of the physical system. So I talk about cyber physical system as the key concept in Industry 4. But what is it? Well, cyber physical system, as it implies, has got cyber plus physical, and that form a system. So it's one system that has got physical elements and cyber elements. When you have both, that means the virtual digital worlds and the real physical world. Once you have these two different worlds, and when you combine them and you marry them, then you become a far more, excuse me, far more complicated and sophisticated but capable system. So that gives you CPS. Well, CPS will give you total connectedness. That means you can easily connect things from one to another. But you connect things also through intelligence. That means intelligence can be communicated or can be generated through this connected world. So we'll have a diagram in a minute to explain how that can happen. Once you have everything's connected, and machines and to machine communications can be made fairly easily. And the communications are the type of semantic communications. That means it's not just simple data transferring from A to B, from machine A to machine B, but rather machine A can talk semantically to machine B, meaning they can exchange concept, ideas, and they can have dialogues. The kind of dialogues that we can have between human being. So it is high-level communication. So we are now talking about a different level of communication that is only possible when we have CPS, when we have a system that combines physical and digital worlds. If we're talking about manufacturing, clearly it's a production system. So CPS becomes CPPS, cyber physical production systems. So I think in this case, we don't make distinctions. We refer to CPS as CPPS when we talk about manufacturing systems. Now, this is the diagram I mentioned just a moment ago regarding the connectivity between your systems. This is a diagram showing the difference between cyber physical system and Internet of Things, IoT, that is. So if you look at the physical level, the green section here, that's the physical world. You can connect different physical assets, for example, machine tools, through whatever way you may have. It could be wireless communication, it could be Ethernet cables, or maybe field bus as well. So then you can have some level of communication, data exchange. So we've got that. We have had that for some time. So that's what I call IoT. But if we develop a digital counterpart and digital twin of these physical assets, so for each one of them, we have a digital twins or cyber twins. Then if we combine them together, we marry them together to become a CPS. And for every single asset, we will have a CPS corresponding to that. Or instead of addressing these physical assets, we are going to address each one of them in their CPS form. So that means we are going to have CPS machine tools or cyber physical machine tools, CPMT, which is the area we've done a lot of research in. So we do the same, and then essentially if you have 5 pieces of assets and then you develop your cyber twins and then you put them together, combine them, you have cyber physical system, then you will have 5 cyber physical systems corresponding to the 5 physical assets. Now, the important thing about this is the communication between the digital counterparts and the physical part there. So it's bi-directional communication. So this will make sure the physical asset plus the digital, they become one unit, if you like. So there's a very close loop communication between the two. Once you have this, all the communication happens between these assets will not have to happen at hardware level, at the physical level. It will happen at the cyber twin level. It will happen at a digital twin level. So the communications will happen at a digital level, and that will make things much easier, will make tasks of communicating with each other much, much easier. And also in this cyber twin or digital twin, we can actually develop some smart algorithms and functions which can analyze the data coming from the physical world, but also make decisions at the digital twin level, and then advise or instruct the physical assets to perform certain actions. So really we're looking at a brand new scenario, if you like, for any machinery we have in a factory. It could be machine tools, it could be robots, it could be AGV, it could be conveyor system, or anything you may have. But as a matter of fact, you can actually develop digital twins for the processes as well, and for the operators. So we'll come to that in a minute. Okay, so it's sounds like an interesting concept, and it has it makes a lot of sense. But has it attract people's attention in the past, or has it attract a lot of publications? Well, the answer is perhaps yes. One thing to look at to get the answer about a particular piece of technology is to have a look at this Garner's hype cycle curve. Assuming that you've seen this, which has been around for ages. So what this curve does is you have the time axis, which is the horizontal axis, and then you have the expectation as a vertical axis. So every single piece of technology from its infancy stage will go through a curve something like this. That means it will experience a steady increase of the public expectation, and then it will come down to some sort of trough of a disillusionment, and then it will come back. So the end part, the tail part of this curve, indicating the technology has made its way into commercial world. So it's generating value, generating revenue, providing benefits to people. So really, you want to see a technology travel through the curve as soon as possible, and in the end up in this plateau of productivity. So I can talk about this curve for some more time, but we won't have the time to do that. So the question is, where is digital twin? Well, as it turns out, in 2017, digital twin is somewhere here halfway before it reached the peak of inflated expectation, if you like. In 2018, it's sort of gone to the top of the curve. So you may say around 2018, 2019, digital twin has reached the peak of expectation. So that means we're coming down the curve now. So that's 2018, so it's more or less right at the top. 2019, this is the only one I can get, which is the cycle for Internet Things technology. So it's come down a little bit, just past the peak in 2019. So one would expect 2020, last year and even this year, I think it's traveling down here, perhaps quicker than we expected, and it's going to make its way into the commercial world, reach the plateau of productivity very soon. So if you search for a graph for 2020, you wouldn't see digital twin here, but I guess it's somewhere on the downward slope. But what you start to see are things like citizen twin, digital twin of the person. So you can see it's looking at the digital twin technology for people, not only for hardware, for manufacturing systems such as that. 2020, we see things like digital humans there. Now, the symbols are all different, corresponding to different technologies. And here, digital human is an orange triangle, which means it will take roughly about, well, more than 10 years before it can go through the whole curve to become, to reach the plateau of productivity. So more than 10 years, it could be 20 years, could be 30 years. And some will actually take less time. So if you see some of the light blue dots, it's telling us it will take about 2 to 5 years to travel through the entire cycle. So it's a useful kind of technology prediction to have a look in terms of knowing more about the technologies, where it is going. So that's the curve, which is, I mean, the idea is to just show that digital twin has been a really hot topic and still a hot topic, but I think we're coming to understand that there's still a lot of work to be done before it will become commercially applicable technology, if you like. Well, that's why we're all doing research in this area. So that's digital twin in terms of emerging technologies. I want to talk about the some of the surveys we've done. So this is a survey we've done based on the Web of Science core collections. So this is called local citation score, based on local citation score. So I'll just quickly go through this. There's quite a bit of details here, but I won't dwell on them for too much longer. So the way we've done that is we just go into this Web of Science core collection, put in some keywords, we'll search the entire database for publications in this area. We found something like 3,300 papers, records. And so we export all of them. We input that into a bibliometric analysis tool, which is HISCite. In that, it will analyze the data. What it does is it will recalculate the citations based on only these 3,300 records that we have found. So clearly the citation numbers will be lower. That means a paper is cited by one of these 3,300 papers. It will be counted as a local citation. So I think by doing that, we perhaps exclude citations from maybe minor journals or non-mainstream journals. Maybe we exclude citation from a conference paper as well, because that probably won't be collected, won't be indexed in Web of Science core collection. So this will give you perhaps more credible data about digital twin and the highly cited papers, the journals publishing these papers. So I'm just going to go through some of the graphs that we managed to plot based on this 3,300 local collections. So this one shows number of publications in Web of Science core collection. So you can see there, starting somewhere around 2004, we start to see publications in digital twin area. But nothing really happens much until 2016 and 17, and then just rocketing up to 2021. We have something like 1,200, 300 papers. So you can see it's a very steep climb in terms of publication numbers in recent years. Out of these local collections, which paper has received most citations? So we've listed all of them, we ranked all of them. These are the top 5 papers. So in other words, if you want to know more about digital twin technology, perhaps start with these 5 papers, and they've got most citations. Interestingly, you can see 3 out of 5 papers are from conferences. This indicates the technology is on a rapid kind of updating stage. So people do not want to wait to publish in a journal, which could take a year and a half, sometimes 2 years before a paper sees the light. So they tend to go to conferences. It will provide a more rapid dissemination of the technologies. So if anything, I think that's perhaps the reason. This diagram, this graph shows the top conferences that publishes digital twin journals, and you can see there CRRP CMS conference on manufacturing systems, and that published the most papers in digital twin over the past years. And that is IFAC conference, flexible automation and intelligent manufacturing, Pham conference, and conference on learning factories. Well, you probably will say, well, a conference should publish more than these papers, but remember, we only source papers that are within this local collection, which is 3,300 papers. The other question is, which journals publish the most papers in the domain? Well, we find out that IEEE Access published the most papers in that. It's a journal that managed to quickly publish papers compared to other journals, but that's actually a Q2 journal. So of importance journals are Journal of Manufacturing Systems, International Journal of Production Research, both are Q1 journals there. And so these are the, if you like, key journals that published papers in this area. And then there's a few other Q1 and Q2 journals in the top 10 journals that publish digital twin research work. So this perhaps also tells you if you have a piece of work you want to write up and publish and show where perhaps to submit your paper to attract the most attention. Sometimes overall. Well, so that's the survey, the review that we've done. So I'd like to move on to talk about the topic, which is digital twin. I think that as I alluded to at the beginning, there are just many definitions. You know, every single paper on digital twin, you go there, read it, you probably find a definition. But I think there are two things on this technology that is of importance and that is of significance that we need to consider. One is the level of digitalization, and the other is the integration intensity. Well, they probably mean the same thing. But they are reflected by actually three terminologies that people often mix together and just call them digital twin. But I think I like to perhaps separate them into digital model, digital shadow, and digital twin, which has got a reason that I'm going to explain to you. There's no point to argue which one is more complete, which is more suitable. They exist for different reasons, and they exist for different applications. So they all have their use. Depending on the applications, you probably will develop one of these three different type of digital entities. So in terms of digital model, that's been around for ages, and those who actually remember computer-aided design tools and systems like Pro Engineer, CATIA, Annex, SolidWorks, well, they're there to create digital models. That's been around for ages. So they create a digital model for perhaps a machinery, a piece of machinery, or perhaps for a product you want to make. So that means you have the physical object, and then you create a digital object. In many cases, it's just a CAD model. So it has got geometrical information. Sometimes it has got materials properties, and other times it has got assembly constraints, and perhaps has got tolerances requirements and surface finish requirements. That's all fine, and we've got that. But there's actually no data flow automatically from the digital object to the physical object. Well, clearly, if you design something and you haven't made that physical object, so you wouldn't have that link. Now, if you want to create a link, very often you have to do that manually. So that's digital model. We still use it, it's still useful, but it's not quite digital twin because it does not have a kind of data communication between the physical part and the digital part. So that's digital model. And the next in the line is digital shadow. What shadow meaning, it has got closer kind of connection to the physical object, if you like. Well, in a sense that the data flow is automatic from the physical object to the digital object. But digital to physical is still manual data flow. So this is really what we're saying here is that digital object is now a shadow of the physical object. So whatever physical object does or functions and do things is going to automatically be reflected in the digital object. So that's why it's a shadow. So this is actually quite useful technology. I'm going to just demonstrate one example that's been developed in our laboratory, maybe two of them. So that's shadow. Well, still there's leaving the communication between digital to the physical part manual. Then, of course, we have digital twin. This is really looking at data flow in both ways automatically. It's very important to have the data flow from digital to the object, to the physical object. This is so that you can actually make some decisions, and then you can optimize your physical system or the product, because you're making decisions in your digital twin parts. So this is perhaps, if you like, the ultimate paradigm for digital twin technologies. And clearly it's not easy. It's not easy to do this. So a logical sequence will be developing a digital model, then a digital shadow, and then the digital twin. So that will be a natural sequence. But I should still emphasize that all three type of kind of digitalization methods, they all have their use and their benefits in different applications. Right, so that's the three levels of communication, or different level of integration intensity, if you like, and this digital twin has got highest integration intensity, if you like. Okay, now I still want to go back to the definition of digital twin. As I said, I won't go into debating each one of them, but I'll show three of them, which perhaps demonstrate the journey of the technology it has gone through. The very first one, it was in 2010. So it's a definition by NASA. It basically says it's some kind of simulation of a vehicle or a system. Okay, and it makes use of sensors, models, and fleet history to mirror the life of its flying twin. So this is really, I mean, a definition specifically geared toward NASA applications. It is a simulation software which try to reflect whatever happens on the physical side. So this is perhaps, if you like, strictly speaking, not a digital twin, but digital shadow. The second definition is from an IEEE conference. This is really emphasize the ability between the physical parts and then the virtual parts, that the communication capabilities. So this is the first time we talk about communication between the two counterparts, the physical and the digital counterparts. This definition number 3, I think, is perhaps a more complete one. Is talking about using multi-physics and multi-scale, still probability simulation model, but it talks about a digital thread. So digital thread is the set of data that you define that will be communicated between the physical and software entity. So that's very important. The other aspect is that the digital twin has got the predictive capabilities. So it has got decision-making capabilities, and that's why it can predict what's going to happen on hardware parts. The third aspect of this is it does talk about over the life of its corresponding physical twin. So that means your digital twin is going to be a living object throughout the entire life cycle of whatever that physical entity is. So that means digital twin will have to get updated from time to time so that it will reflect whatever the physical counterpart is or the status it is at. So that's the definitions, and if you like, I don't want to go into other definitions, but I think these three are actually good enough. What are the examples of digital twin? Well, it could be digital twin for manufacturing. That's a lot we've done in our lab. And it could be for products, and could be for manufacturing assets. So these are the machine tools and robots. And it could be people, as I mentioned. So before too long, we will see digital twin of people, a twin of you, for example, and digital twin of networks. Okay, so we come sort of back to the concept of cyber physical system, which is the key concept under Industry 4. So we talk about digital twin. So really, you have the physical worlds, and then you have the cyber worlds. You combine both together, you have the cyber physical system. But we did emphasize the added functionalities in the digital twin area. So it has got information models and capabilities, and has got knowledge base in there as well, so that it can make decisions, it can do different type of analysis. If it is a fully fledged, matured digital twin, we are looking at a lot of advanced functions embedded in the twin, so that it can actually reflect, you can actually influence the physical world. It could be machine, it could be product. So that's we'll come back to the concept, you know, and we started from Industry 4 and cyber physical system. Then we talk about digital twin, and we'll come back to say, how does digital twin make a cyber physical system? But how do you develop a digital twin? Well, it's actually not difficult to understand. First of all, you need to develop a digital mirror to reflect your equipment or products. And then you need to establish the communications between the two. And the third thing is really you need to work on the data, both coming from the physical entity and the virtual space or digital twin, and then make decisions for the entire system. So roughly the 3 phases of developing a digital twin. Well, we talk about communications and you know, how the physical parts communicate with the virtual parts. Well, there are actually many different mechanisms. So the paper that we just got award for talk about some of these twinning mechanisms in detail. I won't go into the more technical side of that. But typically, you probably will rely on some field bus network or Ethernet-based industry communications or industrial wireless communications and networks. And typical ones we often see is MQTT, OPCUA, and MT Connect. So there are different mechanisms out there, and different applications tend to use different protocols. Okay, so that's digital twin. How do we define that and the applications and the twinning mechanism? I think the next topic I want to quickly cover is the international standard I mentioned at the beginning. So there is international standard. But before we look at that digital twin standards, these are the standards, mostly ISO standards, covering the spectrum from design all the way to manufacturing and inspection. So that's the time axis there. You can see OPCUA standards are here. So the digital twin framework for manufacturing that was published in October last year, ISO 23247. So this is actually the most recent standards in the design and manufacturing area. So go have a look at the standards. It does give you some ideas about how to develop a digital twin. So I'll just quickly go through this in the interest of time. It talk about elements of observable manufacturing elements. These are the physical elements, machines or robots, and then the digital elements. So to make distinctions of these two, clearly the digital elements are the digital twins. Observable manufacturing elements, it could be people, equipment, materials, and facilities. Digital entities, it could be product itself. There will be a digital representation of the products, and could be the process as well, and the applications that we may see. So quickly go through this. And this is so if we have the physical asset here, observable manufacturing elements, you can develop digital twins. So each one has got digital twin there. And then you can develop application on top of that. And then they give you a number of benefits there. Things like planning, validation, scheduling, managing dynamic risks, cost reductions, and so on and so forth. Now, the standards, as it was developed during the process of developing the standards, and there's a lot of industry case studies done to support the development of the standards. One of them is the work with Boeing when they produce their wing structures, and often they need, this on-fly technologies, in situ capabilities of measuring and machining, or what they call the robot drill and fill. So by developing digital twin, they can facilitate that process and really cut down the time for the wing structure manufacturer. Okay, I think I'm coming to the end, but before I finish, I just try to give you some examples that we've done in the laboratory that I'm from. I'll just give you a quick look at a bicycle we developed, the digital twin for it. And then we developed digital twin for machine tools. And also we've managed to retrofit a legacy robot for digital twin technologies. Okay, so first up is bicycle. Now I won't talk about the entire poster here, but I just want to talk about the way that we developed digital twin for the bicycle. So here, basically, it's saying that we've got a real bicycle and we've got a twin digital model of that, and they actually combine together. So I just want to show the digital model itself. Now, sorry, can I ask you whether you can see this? Dr. Samir?
Yes, we can, yes.
Okay, good. Now, this is a SolidWorks model of a bicycle. So you can have a model, but you need to reconfigure that to define different connections and joints. So that will be step one. So if you like, we start from a digital model. And then we move on from digital model to a digital shadow. Okay, so here is how we define different connections of different parts. So I'll just speed up a little bit. You can see different parts are being highlighted, and then you define different connections. The reason we want to define different connections is that we're going to have sensors on the real bicycle that's going to produce the data that will be linked to different parts of the bicycle. Okay, you can see the wheels spinning there. That's because the data is driving the wheel spinning. So in the end, we want to see the bicycle being driven. The digital model is driven by the physical data coming from the physical model. So this is the student's arrow. He has done the work. You can see the bicycle here. We've got sensors around that. It's communicating with our digital twin using Bluetooth. Now I just speed up a little bit. So you can see the sensors there, and on the bicycle, and you can actually use your mobile phone to check the data coming from the sensor. You can see the data there. That's from the sensors on the bicycle, and that data actually goes into the digital model. Then it becomes a digital shadow. And because you have digital data already, you can easily using augmented reality. You can see where he's pointing his phone to the bicycle, and then the data can be overlaid on different parts of the bicycle, and in real time demonstrating the data that's coming from the sensors. If somebody's riding the bicycle, you will see the data changing, of course. So that's some advantage we can have with this digital twin model. Now just quickly go through the second example, and this is the machine tool. So machine tool itself has got a lot of moving parts and different components, so we developed a digital twin for it. We had sensors, in this case, fitted onto a little desktop machine tool just to do a prototyping exercise, and then we can get the data from the machine tools into the digital twin. You can see the data is about different axes, speed and feed rates, and the position data as well. And you can overlay the digital data using augmented reality. Once again, support your production process, so you can basically see the things you wouldn't see without the digital data there. You can see the toolpath is being overlaid here. The last example is retrofitting a legacy system, which is a cooker robot. I think this is about 20 or 25 years old, I think. So it's a robot that's been around in the lab for ages. But what we've done is we've put in a Wi-Fi enabled chip, which is ESP8266, which has got Wi-Fi capability in the controller through serial communication. Then we use MQTT protocol to communicate through the clouds. So you can actually get the data from the actual robots. So I've just got, again, a video here, if I can just show that, which is the final one. See, this is the visualization that we got from the clouds. That robot has communicated to the cloud, provide its moving data there. You can have multiple clients there, of course, accessing that server. You can see here's another one, and that's the real robot that's moving. And of course, it spits out its motion data as well. So that data is now through clouds and driving the digital model. So this, if you like, is a digital shadow. So this will be a shadow of the real robot. And you can see different axis data here is changing all the time, 6-axis robot. So that's an example. We could actually go from the digital model to the physical robot as well. So I won't go into details of this. So this is a test that we could also go the other way around. Right, okay, so let me finish by saying a few final words. First of all, I think Industry 4, one of the key concepts in Industry 4 is cyber-physical system. And the key in cyber-physical system is the digital twin technologies. It's still a hot topic around, if you search around. We acknowledge different views on digital twin, and that's why we talk about digital model, digital shadow, and digital twin. I touched upon ISO standard, which is just hot off the press. If you're really keen to do research in this area and trying to see what international standards are providing, and that's probably where to go. And now we finish off with 3 digital twin examples that we developed in our laboratory. So with that, I'll finish off, but leaving this to you, I wish to acknowledge some of my colleagues and my students who contributed to the case studies that I've just shown you. We will also have a virtual tour of our lab and our website as well. You can scan that. Our website is listed here. The address is listed here as well. So with that, I apologize for overrun the time, but I hope we still have questions. I still have time to field some questions, and I'll be happy to answer any questions.
All right, just maybe 5 minutes. We've got a couple of questions that are on common concern. These are can be summarized as what are the possible constraints when you have to deal with digital twins in real time for small applications, and later maybe for more complex applications. What are the possible alternative way in control to get the real time real?
Yeah, that's a good question. That's a really good question, because if we are talking about manufacturing, we're often talking about real-time control, real-time motion capability. Well, digital twin depends on what it's used for. If it's to do with motion control, clearly there's not much you can do. Clearly, I mean, it would be hard to have the twin in the clouds to communicate with the physical machinery to guarantee real-time capability. But the way it is going with digital twin technologies is that we are looking at edge computing, not cloud computing, but edge computing, which means computations can happen very close to where data is generated, or it's very close to the hardware. So that way you can have digital twin, the computational capacity doesn't need to be that much. So you can guarantee a high level of synchronization. Well, another popular area of using digital twin is for maintenance. But very often if it's for maintenance, there's no requirement of real-time response. So that's actually a good area to implement digital twin. Real-time is a good issue. And if you remember, I talked about the digital twinning mechanisms. So depending on what protocols you're using, you will be able to achieve different levels of time sensitivity.
Right. There was a question about committees and standards, but these were during the presentation shown. Other questions are related to common sensors that can be used for digital twin, but this is also for any type of sensor where you can get information. The other key question is, how is the industry readiness to implement any digital twinning in production for complex parts, for example?
Well, as I've shown, there's a Boeing example that's already happening. So some industries already implementing. They, as I mentioned, they tend to implement in processes that has got non-real-time requirements. It's easy application to take. It's like a low-hanging fruit. So the communication is perhaps not that essential in terms of real-time capability. Maintenance, as I mentioned again, that's already there. You know, we at the moment, as we speak, we're working with New Zealand Navy. So their frigates, their warship, one of the important system on the warship is crane. So they have issues to do with the crane in terms of performing maintenance and to predict its performance and to monitor its performance because it's working in much sort of it's a rough scenario open in the sea. So we're developing a digital twin for crane on the warship.
Right.
But that's clearly there's no need for real-time capabilities. So that's probably where one would start.
Okay. We've got another maybe final question here. Did you ever use a finite element in a digital twin, or have you seen any application? That is
Well,
with time issue here also.
Yeah, well, finite elements that's been seen in digital twins. ANSYS, I guess, they claim to have developed a platform for digital twin. Clearly, they use their traditional ANSYS FEA model to predict performance. That's right. Yeah, no, that's part of that. I didn't talk too much about that. I was focusing on machining, the process control, but prediction over performance of a piece of machinery or simple components, you will have to do analysis such as that. Yeah, no, that's clearly a critical part of digital twin.
All right. With this, thank you very much, Professor Xun Xu, for the nice and informative presentation. We'll move maybe to the second presentation. We are a little late in terms of time. We'll take over maybe some of it in the break. We catch up with the break time maybe. So the next presentation is by Professor Sharif Ullah or Sharif Ullah. His talk is about developing manufacturing systems for Industry 4.0 and beyond. Professor Sharif Ullah is full professor at Kitami Institute of Technology in Japan. He is now direct KIT's Advanced Manufacturing Engineering Research Lab and Manufacturing Center. He is also the chairperson of the Intelligent Machines and Biomechanics Department. He now serves as the Award Committee Chair of the Manufacturing Systems Division of Japan Society of Mechanical Engineers. His research group focuses on smart manufacturing, 3D printing, sustainable product development, reverse engineering, and so on. He has been conducting joint industry-led research with multiple manufacturing companies, and he has mentored many graduate students. He has published many technical articles in reputed peer-reviewed journals, edited books, and conference proceedings, and he has been serving on editorial boards of several peer-reviewed international journals. With this, without further delay, Professor Sharifu, the floor is yours, please.
Thank you so much, Professor Samir. Could you hear me? Is it
yes,
okay?
Yes, we can, yes.
Okay. I didn't know that you invited Professor Thati because he's our co-authors of our papers. And we have been working with Professor Thati for the last 15 years.
Yes, he is with us since this morning.
Yeah. Professor Thati, how are you?
You are muted, or maybe he is busy.
Okay. So today I would like to talk about 3D printing and Industry 4.0. I mean, 3D printing is also part of Industry 4.0, I guess. So since you introduced me, I will skip those parts. As you know, Industry 4.0, there are many expressions. Germans, they say Industry 4.0. Americans, they say smart manufacturing. Japanese, they started saying Society 5.0. They want to be ahead. So the thing is that they are trying to say that, okay, we need to cherish what ICT technology is giving. And for Industry 4.0, we are talking about big data, digital twin, as professors who explained, cyber physical system, cloud computing, and so many things, machine learning, artificial intelligence. So these are the words you will see. They always come with Industry 4.0, smart manufacturing, Society 5.0. And there are many narratives. So, but the thing is that I would like to show you a little bit in a different way. This is the diagram that if you open the book of the Global Manufacturing Revolution, Product Process Business Integration and Beacon System by Professor Coren. So basically what he is trying to say that we are actually making a U-turn. Yeah, I mean, previously all the products were made by craftsmen, and craftsmen can handle many varieties of product with small volume. And then we went for mass production. And after mass production, we came to mass customization. And then after mass customization, we came to regionalization or personalized production. Regionalization is a very important issue. For example, this year, if you see the US market, Toyota is the #1 car selling. I mean, their cars are sold because, you know, during this pandemic, Toyota could manage their production because 80 to 90% of their parts they are making inside the US. So their supply chain is actually regionalized supply chain for North American market. So regionalized production is actually one of the key issue that will come. And personalized production also, I mean, one of a kind product. This kind of thing, will be very important from now on. And for supporting those things, we need some sort of systems or machine tools that is universal. I mean, we can, whatever may be the shape, we can make it by one single machine. So this is, that's why 3D printing and these kind of machines are very, very useful, I would say. For example, this pump. This pump, we made it by 3D printer. Otherwise, we could have, we had to use many manufacturing processes to make it. So the additive manufacturing will become one of the very important player of Industry 4.0 or whatever you say in smart manufacturing. And we have many additive manufacturing processes like sintering and fuse deposition. So for example, this one is a pump. This is fuse deposition. This is a different additive manufacturing process. So one of the things that this pump, I could make a single unit using 3D printing technology. That is not possible by other subtractive manufacturing processes. The other important aspect is socialization of your manufacturing. I mean, well, manufacturing will be done by very highly skilled person and so on. So this is going to change. You will see all over the world, there will be a lot of fabrication lab where you walk in and you try to give an idea of your product. Just suddenly it will be digitized and produced. So this kind of socialization will come into being, and 3D printer and this additive manufacturing technology is going to be a very important driver on that. For example, in our city, the Starbucks, besides Starbucks, there is a fabrication lab. A lot of 3D printer, high school, middle school guys, they go there and make whatever they like. So this socialization aspect is very important for this new technology. And another aspect of 3D printing, that we can make porous structure or this kind of scaffold using 3D printing technology. And most of the times what we do, we actually use off-shelf CAD packages like this one. We have unit cell, then we create the scaffold, and then we try to print it out. And we can use metallic or plastic printing method as we like. But the thing is that there are more complex structures in the nature. For example, here I'm just showing you two examples. So the bottom is a coffee filter made of ceramics, and the upper one is a pot by which we do a bonsai. You know that the small trees, we Japanese love to make bonsai. So if we see their porous structures, it's not like scaffold that we designed by our software. So we are trying to build a capacity on that. We have actually created a lot of porous structure for many applications, for veterinary doctors, for soilless cultivation, and for say tool shank with nice vibration control and so on. So this kind of structure actually, it's very difficult to make using off-the-shelf softwares. We are developing some systems by which we can do it by ourselves. Say we would like to make a porous structure. Can you see the video, please? Can you confirm? Is the video is running?
Yes, we can see.
Okay. So this is a simple structure, non-porous structure. We would define the porosity and the fineness of the pores. The system creates some porous structure like this. And we can export its STL data and print it out. So for example, this is one example of that one. So this is actually, we did it for one of our colleagues who is trying to develop new heat transfer mechanism for electronic devices. This one, we developed another system actually that is for soilless agriculture. We have a non-porous structure. We just create some point cloud, random point cloud around that structure, as you can see. And then we fill the random spaces using a polyhedron and tetrahedron. And finally, we get the structure we want. And we have this STL data by which we can run our 3D printer. Very simple. User don't have to do anything. Just 2 or 3 clicks. And this is a software also we developed by ourselves. We can analyze the cross section of a porous structure, whether or not it could be made perfectly or not. So we also did try to develop some system by which we can ensure that, look, whatever maybe my design, we could make it properly. So this is a study that one of our students is doing now. He is trying to create a porous structure, and then he made the porous structure with different fabrication height, so that he can take the real cross section of the product. And then we use micro CT scan to see the whole internal structure, whether or not it is okay with, conforms with our design. And we try to see where is the problem. So if we see there is a problem, then we go back to the design and try to fix it up. Usually for this kind of structure, we have problem with loose shell or thin wall, or sometimes fabrication errors. As you know, the most advanced software is given by Materialize, Belgian-based company. They always say that, look, your porous structure is not printable, but unfortunately, this is not true. Or fortunately, it is not true. We always try to print it out, and we see that there is almost no problem with the fabrication. So we are trying to develop this kind of software by which we can actually compare online and give some feedback to the designer so that he can stop or modify and so on. So now let me talk about Industry 4.0. Actually, 3D printing is also part of Industry 4.0, but let us give a name Industry 4.0 at this moment. Industry 3.0, the main point was, this course I have been teaching for our master's student for last 5 years, and the students from many other universities, they actually take this course online. So the first thing I have to tell them, like, what is the difference between 3 and 4? The 3 is actually basically automation, and you say that your human is not good. Human takes money, you have to pay salary, and so train him and so on. So let us automate. But in Industry 4.0, actually, we don't say that human is bad. Human is also an important part, and we try to, we try to, reinforce human by using all those technology, not discarding human in the loop. So that is actually the spirit of Industry 4.0. And end of the day, what happens? We jump to open system from closed system. So there are many aspects of closed system that actually we cannot use in open system. So today, since the time is limited, I will not talk about this. We actually covered it deeply in our course called Industry 4.0. I think Professor Xu has correctly articulated while he was talking about the digital twin and so on. But for my presentation, I would like to use this articulation of Industry 4.0, or they call it human cyber physical system. Of course, we have physical systems, so we have human, and we have middleware called cyber system. The most important part of this system is self-growing knowledge base and learning based on artificial intelligence and so on. So this two is the most important part of human cyber physical system, or Industry 4.0 as a whole, you can say. So, okay, fine, self-growing knowledge base, but what is knowledge? This is the fundamental question that we need to answer. So unfortunately, we didn't find any answer to this in our extant literature. So what I did, I actually closed all the books of our ICT technology and so on. I went back to 300 years back, where actually human intelligence was deeply studied by a lot of philosophers. One, I can say David Hume, Scottish philosopher, and his book, An Unique Inquiry Concerning Human Understanding. In that book, he said that there are two kinds of knowledge. One is relations of idea, and the other is matter of fact, that our experience. And later on, critique of pure reason, Immanuel Kant, he said that relations of idea are two types. That one you cannot challenge, it's always true, tautology. And the other is sort of relationship idea that can be falsified. So this was actually my findings, that these two gentlemen is actually really, they went into deep and tried to figure out how human actually learn. For example, most of the cases we say that all cause, all effect has a cause or something. The causality and cause effect, these are actually human, what do you call, it's not in the nature. I mean, we human being bring while we are trying to explain our things. So this is very interesting. You can go and see. The other thing that I found is talking about knowledge is in the literature of education, particularly the acquisition and retention of knowledge, a cognitive view by Ashbel. Ashbel was a doctor. I mean, he was a pediatrist. So he used to see the kids coming to his clinic, and he used to observe them, how their vocabulary is building. So that is also a very nice book you can see now. And based on Ashbel's idea, learning how to learn, the book was written by Novak and his colleague. And Professor Novak is actually developed something that we call concept map. So using concept map, the NASA is actually training their engineers. All the technical issues, when they teach to their engineers, they use actually Professor Novak's concept map, which is coming from Professor Ashbel's idea. So anyway, so based on that, I wrote one paper that what is knowledge in Industry 4.0. So this is actually gives me the idea of what is knowledge inside my self-growing knowledge base in the cyber physical space. And I have given examples from manufacturing so that you can understand. So please go ahead and see when you have time. So what I said is that knowledge actually we cannot define by a single term. We need three things: claim, inference, and provenance to articulate a piece of knowledge. And most of the cases we just articulate the claim, but we never bother about the inference and provenances. And I said that there are four kinds of knowledge: definitional, deductive, inductive, and creative. And most of the artificial intelligence is actually talking about inductive knowledge. I call it complex inductive knowledge. There are three kinds of inductive knowledge, and I call this artificial intelligence-based knowledge is complex inductive knowledge. Anyway, you can go and see. So if I go back to the slides, they are saying that self-growing knowledge base should be there. There should be some artificial intelligence of learning and so on. So now we have the know exactly what is knowledge. Now we have to, when we build system, we try to figure out everything based on this knowledge-aware network of our information. So this is one narrative that we always give to our students, that look, we for human cyber physical system, we should have this enabler network connected by internet, and we should have some sort of a data acquisition system or big data, whatever you call, and there must be self-growing knowledge base. And from where we get this knowledge? Okay, we know the classification, but from where we get? Our idea, in a very narrow sense, for example, for machining or manufacturing process, we see that there are three kinds of digital twins: object, process, and phenomena twins that actually provides the knowledge. Therefore, we need to construct the twin, and we need to adapt the twin into the system. In that way, we will have this self-growing knowledge base. The more digital twins you can construct and inject, the more knowledge you will find. And there are 4 forms of knowledge. And okay, what is digital twin? I think Professor Xu has given a nice representation of that. I just add in that sense that if I would like to construct a twin, I have to construct 5 modules. One is input module, the other is output module, by which the twin should communicate dynamically in real time. And there must be a modeling module by which we model our object or process or phenomena. There must be a simulation module by which we actually reverse engineer that phenomena. And there must be a validation mechanism. We have to know that whether or not everything is going fine, there is no error, and so on. And this is actually some of the user interface of the digital twin construction system. Like, for example, if we say that I would like to buy a car, before I buy the car, I have to build it. So if I would like to say that I will have a digital twin in my system, cyber physical system, I must have to construct. So we are actually developing the tool by which you can construct. So this is the user interface 1, 2, 3. I'm just showing you. There are many, and if you go to our publication in the Journal of Industrial Information Integration, where Professor Thati is also a co-author, so you can download its free open access, and you can see how we build up this. And when we use the twin, we try to see that whether or not it has a real-time response. I think in the last presentation, there was a question that how much time I should give. For this kind of phenomena, we see that 0.2 millisecond or 0.3 millisecond. If we wait for that more, we cannot handle. So the very high response we actually got it. So please go ahead and see and download and expand on that. If you have any criticism, or if you have any question, or you want to work with us, we are most welcome. So I have no time to explain the whole bunch. I will just talk about the input module. That is actually the very important issue for digital twin. And we were trying to use almost what you call natural language type of expression to build this input module, because Professor Xu has shown that there are many ISO standards available. So we would like to break those standards, we think that in Industry 4.0, each person will have his own way of talking or standards. So we never mind whether he follows the ISO standard or he has his own way of expression. So we are trying to see that, okay, how can we build this input module or organize all this information based on natural language? For example, I give you a very simple idea that turning the surface roughness, environmental burden, tool life, machining time, evaluation, performance. These are some concepts that came into my mind. If I organize them, it will create a sentence. Performance of turning can be evaluated by machining time, surface roughness, tool life, environmental boundary. So this way, actually, in the job floor level, we see that people are talking to each other and they express their views. And if we can put all this information with this sentential expressions, then it is very easy for human to understand, and also for machine. We can easily make an XML data out of that, and this XML data can be machine readable. So we are trying to actually, what Professor Zhu is saying, that we have to follow the standard. We are actually saying that no, we will not follow the standard, we will break it. So this is sort of wild proposition, and I think industry, at least industry, not for beyond industry 5, will go to this level per se. So so the thing is that, okay, for input module, we will have this XML data, and it should come from our big data. And from where we get the big data? Frankly speaking, there is no big data for manufacturing. The only big data we have now is material big data, developed by Professor Ashby at Cambridge University. Unfortunately, he sold his data to ANSYS. So now you cannot buy from his company, from Granta Design. So for manufacturing processes, or we don't have it actually. We need to build it up. So we are actually working on that. How can we organize the yield structured, or semi-structured documentation so that we can build the big data, and the big data provides me the XML data that can be fed into our digital twins input module. So this is work that we are doing for the last 3 years, and we are hopeful that we will be able to progress a lot. And it would be nice if you can join us in that research. So in the future, what is going to happen is that we will have some sort of iPod where we can see the digital twins, and we have our own needs, maintenance need, or decision-making need, or visualization need, or automation need, or our process planning or enterprise need. So for these needs, actually, we will get the knowledge from the digital twins. And the way I have shown that we have to build these twins based on knowledge-aware concept map, at least for the input module. And if we can do that, there will be no problem with the communication among heterogeneous parties, heterogeneous people and machines. So I think the Industry 4.0 will go to this level very soon, especially as you know that web technology is going to change. Now we are using actually web 2.0. It will be 3.0 or 4.0. A lot of semantics, annotation, these kind of things will be available in this web. So that kind of web technology will help us to build the digital twin and the content that I'm showing you. So I think in the near future, what you will see that you have this kind of distributed, networked, very agile sort of arrangement connected by internet, and all parties are independent with each other. They talk their own language, but they somehow can communicate and provide the information that they need for each other. So by saying this, I would like to thank you for inviting me today and giving me this opportunity to explain what we are trying to do in Industry 4.0. And if you have questions, you are most welcome to ask.
Thank you very much, Professor Sharif, for this nice and informative presentation. I've got one question for you related to I-40 related to 3D printing. Did you try to have access to the STL file and go ahead with modifications automatically, or here, yes, in this process here? Or what was the exact process you went through?
Yeah, for STL data, for example, this one.
Yes.
This one, as you can see, we have only 12 facets. It's very core, very coarse. So in our system, we actually divide these facets into very small facets. We have this capacity here. So we can manipulate whatever STL data we input into our system. We can manipulate based on the porosity level that we want, or the coarseness of the pores that we want.
Okay, so you are securing a closed loop efficient correction.
Well, I should not say efficient correction. What I see is that it's very interesting, you know, all the pores, they support each other. Right. As you know, if you have a vacuum, you cannot add material. But the thing is that the pores are so close to each other and distributed randomly, they actually support. Without support, we can weaken. So what I would say that we are lucky in that sense. Without doing anything, we could actually produce that one.
Right. There was another question in the QA here. Muhammad Al-Saggaf is asking how we can print graded materials. That's maybe a general question here.
Graded material is material with two different, or we will have a gradient of porosity.
Could be a gradient of porosity or different materials combined together.
Yeah, we didn't try yet with different materials, but we tried with gradient porosity. It works very well.
Right. In your slide number 35, when you were talking about a possibility, yes, here to have, there are various applications I'm aware of. For example, DMG or Index companies have already partial I-40 monitoring of processes and production lines. I don't know whether you have seen that, and what is missing in this loop?
Well, a DMG Moriseki, you are talking about.
Yes,
these
yes.
German Japanese companies.
Yeah.
You know, Mr. Mori, I met him at Professor Tati's conference many years back.
Yeah.
And we are talking, and what he's saying is that due to this industry 4.0, all things are connected. So his engineer is actually receiving a lot of information. And he has only 28 engineers to take care of all those machines in Europe. The end of the day, human being has to check. This is the problem that they are facing. And they are actually burdened with unnecessary information. So the thing that I told you, that now we are pretty much on machine-to-machine communication-based syntax or semantics. What I'm saying is that break that one. Try to use natural language like this one I'm saying. So if we have a semantic annotation that is very close to your job floor, activities, it will be very easier for you to figure out the whole bunch of information. So Moriseki is actually suffering a lot, though they will never tell you because they have to sell their machines. But the engineers are burdened with huge amount of information. End of the day, they have to check and give the decision why this problem has happened.
Yeah, I heard a Japanese machinist for high-speed machining a couple of years back claiming that the best way to have a full compensation of any of the errors that can happen in machine tool in the process is to embed the expertise of the machinist. And that embedding of expertise there's no easy way to do it. And I think this is where, in this interface in the human language, human understanding into back into numerical or digital information is becoming extremely important under maybe artificial intelligence to some extent.
And as I said before, you cannot cut human from the loop. If you cut it, you are gone.
Yes. So
how you empower your human in the whole process, that's the main spirit of Industry 4.0.
Maybe 2 or 3 more questions. What prioritization should we make when dealing with big data?
Well, as I said, big data, for example, very simple. Say you cultivate vegetables. Do you after cultivating your vegetables, you have to wash it, and then you have to cut it. Then you have to put it in your dish, right? So big data. I mean, you have plenty of data generating from your machine or your day-to-day activities. But you think that where this data will be used. For example, here we are saying that data will be used. Data will be used for building digital twin. So if you think that data will be used for digital twin, then think about the components of digital twin and prepare some information based for feeding those components. Otherwise, your data will grow up, and end of the day, you cannot use it. It will not add any value to your production.
We've got another question asking what is new in the i50 as compared to 4.
Okay, this is a question that my students also ask me. You know, Industry 3.0 was only for M2M, machine-to-machine communication. We call it syntax. The regimental rule is very, very important. That's why lot of standards are there. But for Industry 4.0, semantics, human involvement is very important. Meaning is very important. What does it mean? And for Industry 5.0 or beyond 4.0, the most important thing will be pragmatics. Whether or not you can build trust on a content, whether or not it is safe for you to bring it to your own vicinity. Nowadays, we always work in an area where we can trust each other. Most of the cases within a company, within a factory line, and so on. So Industry 5.0, we have to deal with trustworthiness of our contents, as well as our ability to implement that things. So we call it in a philosophy, we call it pragmatism. So pragmatism will be the most important part for Industry 5.0 or 4.0, beyond 4.0.
Right. Just one last question, maybe briefly answered, if you can, please. In monitoring 3D printing, what could be the online monitoring online real time, of course? What could be the way to monitor the printed layers. Of course, it depends what we are monitoring, whether the building, the possible expected stress or strength, and so on, or basically structure.
Most of the cases, what we see during 3D printing, what happens is that either it came out from the base, the whole bunch is coming out from the base, or there are some problem with the nozzle. So monitoring the nozzle is most important thing, I would say. So most of the problem is actually coming out from the nozzle area. So that actually accumulates to your layer. So if you can develop a system, say visualization system or camera-based system for monitoring what's happening on the tip of your nozzle, I think it will help you a lot. And it would be very difficult to develop that system.
All right, with this, I thank you very much for your informative and nice presentation today. The next presentation is by Professor Duc Pham from Birmingham. Good morning. We are moving now from Auckland to Japan to Italy. Now we are in UK, okay, in the same line of movement. And by the way, for the attendance, these guys all know each other, by the way.
Yes, yes, correct.
Right. So,
good to see you all.
Nice to see you.
Long time no see, Professor Teti. Long
Yes,
time no see.
Yes, a long time seeing, but we've been in contact. We've been in contact through emails and all of that.
That's right. That's right. Yes, yes.
Okay, so Professor Duc Pham will be talking on robotics, disassembly for manufacturing. Professor Duc Pham is an OBE fellow of the Royal Engineering. He is also the fellow of the LSW, the SME, IT, and the IMECI in the UK. He is a PhD and DEng holds the Chance Chair of Engineering at the University of Birmingham, where he started his career as a lecturer in robotics and control engineering, following undergraduate and postgraduate studies at the University of Canterbury in the New Zealand. And prior to coming back to Birmingham in 2011, he was professor of computer controlled manufacturing and director of the Manufacturing Engineering Center at Cardiff. And his research is in the areas of intelligent systems, robotics, and autonomous systems, and advanced manufacturing and remanufacturing technology. I know that he has led several EU research consortium, among them IPROMS, where myself, when I was in Manchester, was part of it, as well as Professor Teti here. So without further delay, the floor is yours, please.
Thank you very much, Professor Mekid. It is an honor to speak to you. I'm not unfamiliar to KFUPM. I've visited you more than 20 years ago, and I have some friends there, as you know.
Yes.
Bekir Yubas is a longtime friend, and I visited Professor Budaya. I think he's still with you, yes? Yes. Muhammad Budaya, yeah. I visited his home as well. He was very kind, offered me hospitality. So it was a very nice visit many years ago. And it is very nice then to be able to speak to you again today. I'd like to share my screen, please, yeah? And then after that, if you don't mind, I would like to turn off my video because of the bandwidth issue. And at the end of my talk, I'll turn on the video again if you remind me. Yeah.
All right. Okay.
Okay. Thank you so much. Can you see my screen yet?
Yes, we can. Yes.
Okay.
If you do it, if you put it on presentation mode, please. Yes.
Sure.
Okay.
Sure. It's coming, but slowly.
Yeah. It's okay.
All right. Yeah. You can see it now.
Yes. Excellent.
Yeah. Okay. So the preamble is almost finished, and I'll be starting to talk about remanufacturing, and then cover robotic disassembly, which is the main topic, and our auto reman project, and then conclude the presentation. So as preamble, I already said that I'm not unfamiliar to KFUPM, and maybe some of you have not heard of our city. We are the second city in the UK. Now, it is arguable whether we are second or Manchester is second. I have to concede to Professor Mekid that Manchester has more famous football teams than we do. Then, what is remanufacturing? We all know what manufacturing is, which is the conversion of raw materials into the product that we use, and then we dispose of. Now, remanufacturing is part of a circular economy. So you can see the loops going back from the bottom here, where we show the disposal, but we don't dispose of the product at the end of its life. Either we reuse it directly after repairing it, maybe, or we recycle it, which is the outer loop, or in the case of remanufacturing, we take it back and then we remanufacture it and we produce the product that was at least as good as the original product. So that is the definition of remanufacturing, taking a used product and making it into at least the same quality product as it was originally. Now, it can be even better than the original product. As you might not believe it, but it might be even better in some cases. So it is not the same as reconditioning, which is just making it maybe looking a little bit better, or refurbishing, making it look better. But remanufacturing is to produce a product that is of at least the original quality. That's the British standard definition, and it's a standard definition in other standards as well. So as I said, it's part of the circular economy, and because of that, we are interested in what it does for us. But before I cover what it does for us, I just go through the different operations involved in remanufacturing. So here is the end of life product, the product that has reached the end of its service life. The first operation that is done is to take it apart. So it has to be disassembled, and then the components are cleaned, they are inspected, and any faulty components will be replaced or repaired, and then the whole thing is reassembled, tested, and then you have the remanufactured product. Now, why can you have something better than the original product? Maybe at this stage, you could replace an old component with a new version of the component. Let's say a new material, component with a new material which is stronger, lighter, and therefore the final product can be even better than the original product. Yeah, so at least the quality is the same or even better. Now, disassembly is, remember this, is the first operation in remanufacturing. Without it, there won't be any remanufacturing possible. Yeah, you have to take the product apart before you can do all these operations to it. Now, why remanufacturing? You can see here some charts connected with energy consumption and material consumption. In the case of manufacturing a new product, and in this case, alternators and motors, and remanufacturing it. So remanufacturing it, you can see, consumes about 10%, an order of magnitude smaller energy than in the production of the new product. Material consumption, about the same, 10%. So you can save a lot of energy and you can save a lot of materials. So this is one big incentive for remanufacturing, save resources. Here's another case, engines. Our industrial partner, Caterpillar, did a case study, and they found that for this particular model of engine blocks, they save 62% in greenhouse gas emissions. They save water consumption 90%, more than 90%. Energy consumption about 90%. Again, material consumption 99% they can save. And then also something that I've not mentioned, landfill. There is no need for landfill almost, because you don't throw anything away. So 99% savings in landfill requirements. So those are the incentives: environmental, resource, and other things that you can save. And of course, all this translates into lower cost for the manufacturer and lower cost for the consumer. In many cases, a remanufactured product can be 30% cheaper than a brand new original product. I have a little test for you here. I will leave you to look at these two videos for 10 seconds, and then you will have to answer what I'm trying to show in these two videos. What these two videos show. Okay. 3, 2, 1, finish. The left-hand video shows that disassembly, which is a real operation here at an engine remanufacturing company. Remanufacturing is very labor intensive. You can see lots of people involved. Yeah. And then on the right-hand side, also is remanufacturing. Disassembly in particular is a very skill intensive operation. It's very hard to automate. Yeah. So I show two things. It's labor intensive and skill intensive. It is very hard to automate. People try to use robots, but it is not easy, because we saw that it is a labor intensive and it is a skill intensive operation. So robotic disassembly is something that people try to do to solve this bottleneck in remanufacturing. And our research tries to derive some fundamental understanding of disassembly processes. Remember that disassembly is the first operation in remanufacturing. So we focus on it and we try to get a fundamental understanding of it. We are not the first group to study robotic disassembly. The robotic disassembly has been studied for 20 years, but we are the first to look into disassembly as a fundamental operation and to try and apply science to the study of disassembly. So here is a kind of symbol of our project, and you can see it as a background in my photos. Later on, you will see again. And the project consists of 5 different modules. The first one is disassembly science. So it takes us about 3 years, has taken us about 3 years to study this, but actually I can tell you that it can take people 20 years to study disassembly science. So there's a lot of work to do. From studying this disassembly science, we hope to come up with strategies to enable us to get robots to perform disassembly in a reliable manner. So that's disassembly strategies from the science, from the understanding. We want to have robots to conduct disassembly automatically by themselves, if possible. So sometimes they get into difficulties because disassembly of a used product is a difficult process. the product, the condition of the product is not known. So the robot can encounter many difficulties, can encounter many problems. So during the disassembly process, it may have to replan, you know, the plan that you designed for it at the beginning may not be executable. So it may have to replan. So planning and replanning of the disassembly operation is something that we also have been studying. Now we realize that total automation of disassembly is not possible. Is at least economically is not possible, because there'll be cases where it is too expensive to perform total automation. So we look at human-robot collaboration in order to address problems where it is not perhaps economical to use robots to perform disassembly, or when there are technical problems that are too difficult for robots to solve. So we study human-robot collaboration in disassembly as well. And then the final work stream is to construct practical demonstrations of all the strategies, all the techniques that we have designed. So here's the project summarized again. It has these 5 modules. Disassembly science, we look at fundamental operations, basic operations, and we study the forces involved in disassembling, the information that we can get out of disassembly operation, and that we can use in order to get a robot to perform disassembly automatically and reliably. So strategies are devised to enable robots to perform disassembly, these basic operations of pulling a pin out of a hole. And disassembly planning, we look at the ways that a product can be disassembled. And we look at human-robot collaboration, robot-robot collaboration in disassembly. And then we construct a number of studies, case studies. So before we started the project, we conducted a study of more than 400 different products to see what the most common disassembly operations were, so that we could focus on them. So in total, we found something like 12,000 operations, and we classified them. And unscrewing was the largest class of operations that we found, about 40%. Separation is another class, and pulling, like pulling a peg out of a hole, pulling a shaft out of a bearing, was another class of operations. So we studied how to do unscrewing, and in particular, how to do unscrewing automatically. So we look at vibrations as a way of getting things to self-loosen. Now, this self-loosening has been studied also for many years, but in the context of preventing self-loosening. We study self-loosening in order to promote self-loosening in disassembly, and we are designing tools to enable this self-loosening to happen more easily. So this work is ongoing. We also studied the effect of heating on disassembly. So we aged screws artificially. We put them in salt solutions and in saline solutions, and overnight they can become very rusty. And we studied the efforts involved in unscrewing a rusted bolt, and we look at the use of forces, the use of lubricants, and we also looked at the use of heat, and we found that lubricants can help, but heat can help even more. So this work is also ongoing. I mentioned the use of the study of strategies, the use of knowledge that we can derive in the study of the science of disassembly in order to design strategies. So we have looked at strategies for removing a pin from a hole using active compliance. So you can see on the right-hand side, the robot uses force sensing to remove the pin from the hole without the pin getting stuck in the hole. Now, I studied for 3-4 years at the beginning of my career. When I was a PhD student, in fact, I studied the insertion of a pin into a hole. And 40 years later, I looked at how to remove the pin from the hole. So we are talking about circular economy. Sorry, did someone?
Dr. Duc, I think people are not, cannot see maybe the slides. I don't know what is happening. Let me check.
Oh, I'm so sorry. I have not changed anything.
What, 1 minute, I don't know.
You cannot see at all?
I don't know. Can you see the attendance? Can you write on the chat if you can? You can see, yes? Okay, I think they can see now.
They can see. Okay, I'm sorry about that.
No, not yet.
What happened.
No, not yet, sorry.
They cannot see.
They cannot see. I don't know what is happening.
Okay, what I will do, I will stop sharing and share again. Is that okay?
Yeah, maybe, yes.
Yeah. So nothing has happened on my side. So I'll try and share again. Yeah, okay. Yeah, is it working? Can you see the screen? Hello?
I think, yeah, they see now, yes? Yeah, okay, it's fine. Go ahead.
Is that okay?
Yes.
Yeah, okay, good. So now, what I was showing
if you go back maybe by one slide and
okay.
Yeah, please.
Yeah, I'll go back one slide. Let me just see. So I was showing this. Did you see this slide before? Yeah. So I was showing these screws that we artificially aged. We put them in a saline solution overnight, and after one night, they could become so rusty. And we studied the use of lubricant in order to facilitate the unscrewing operation. We found that obviously lubricants can help, but what helped more was the fact we used heat. So heating reduced the disassembly efforts by 20%, by 30%, whereas lubricants only reduced by a little bit. So that was something that we studied. So from our study of fundamental operations, we were able to devise strategies to remove the pin from a hole without getting stuck. Now, why do we want to prevent the pin from getting stuck in the hole? Well, if it gets stuck, it can be damaged, or the hole can be damaged. And if we want to save these components for further remanufacturing, then we want to avoid this kind of damage. That's why we use force torque sensing, and we use this compliance strategy to enable the robot to remove the pin from the hole without damaging either. In addition to active compliance, we also looked at passive compliance. Now, those of you in robotics and interested in assembly will have heard of the use of passive compliance devices for inserting a pin into a hole. Now we look at passive compliance devices to help us remove a pin from a hole without stressing either of them. So you can see we studied these, we did a stress analysis of the movement of the pin from the hole, and with and without the compliance device. So without the compliance device, you can see the pin gets very stressed, but with the compliance device, the stresses are much lower. And we designed our own compliance device. This is actually a device based on my own PhD studies many years ago. Then I looked at the use of this device for inserting a pin into a hole. And now my students looked at how to use this device to remove the pin from the hole. We did not just look at pin and hole. We looked at this operation here, which is sliding of something along a slot. And you see on the left-hand side, the robot is still getting stuck. Whereas the one on the right-hand side started later and has finished. And this is because on the right-hand side, the robot was assisted with vibrations. So vibrations can be very helpful again in disassembly operations. We saw that with the case of unscrewing. Vibrations we can use can be used to help a robot perform unscrewing operations. Here again, we see vibrations can help a robot perform this disassembly operation much more easily, much faster. We don't just teach the robot to perform operations. We let robots learn by themselves. So in this case, we let the robot learn the operation using reinforcement learning. And in reinforcement learning, there is a reward function, R, big R. And the aim is to make R as large as possible by taking decisions autonomously. So the robot performs some trials and errors, and through trial and error, it can discover the way to remove a component in a way to maximize the reward. So here you can see this big reward consists of the smaller rewards R, and a small reward R is made up of these components, and this is the movement. So if the movement can be made so that it is large, and the forces and the torques felt by the components and the robot are minimized, are small, then R will be large. So if you can make a lot of large R's, then this big R will be large. So this is how we make a robot learn its operation through reinforcement learning. And you can see here, the same operation that I showed you before, but autonomously learned by the robot. So here the robot failed. The robot has failed again. And after a number of times, here the robot will be able to reach the end by itself without being taught. Vibrations again. We are interested in removing press fit components. So here, this gray component is press fitted into this hole. And how to remove it is by using impact. And if we use impact at the right frequency, we can reduce the amount of force required to remove the component. So this is something, again, that our team is studying. And you can see here a simulation of that. And here we are not removing a press fit component, but we are removing a component that is wedged. So during the disassembly operation, the component got wedged, and by applying impact onto it, we can unwedge it. So this is something that people do. Intuitively, they can knock a component a few times, and then they can unwedge it. So we study how to do this unwedging by knocking on the component. I mentioned that we looked at disassembly planning. So here's an example. A water pump consisting of a number of parts. The first plan is this. This is the first plan, how to undo the different parts. And then the second plan is this one. And it has the same number of steps, but the third plan is shorter. So through disassembly planning properly, you can make the make the disassembly operation shorter, quicker, so you can save time. So this is a very simple case. In the more difficult case, then an optimization program will be needed. And in our case, we have our own optimization algorithm known as the Bees algorithm. And when you have hundreds of components, then the Bees algorithm will be needed in order to come up with an optimal disassembly plan. I mentioned collaborative disassembly, and the reasons for that, there may be difficulties that are where, for instance, a force is too high for a robot to apply. So a person may be needed, or the force is too high for the person, and a robot and a machine may be needed. And there may be economic benefits. You know, if the batches are very small, you can't devise tools and fixtures to enable a robot to perform a disassembly operation. So a human may be the most economical means of performing disassembly. And sometimes social motivation. You know, you want to replace a human with a robot as much as possible when the task is dangerous or boring and so on. So these are some of the reasons for wanting to have humans and robots employed at times. In our lab, we use a number of collaborative robots. These are not all the robots that we do, that we have. We have only a small number of collaborative robots, and I will show you some demonstrations of robots working, performing disassembly. So the first demonstration I won't show, you can see that on YouTube, is the disassembly of a water pump. So here is the a cell where we have two robots and a machine, and the person operates the machine. This is only a lab demonstration. So we have a manual press, and the press is used to remove a press fit component. So a high force is required, the press is needed, and the person operates the press because it's a manual press. And normally, if only a person is used, then the person catches the part as it comes out of the press in order to prevent it from dropping and let's say, getting damaged. But because we have a robot, the robot can act as a third hand of the person, and the robot goes and catches the component, as we can see here. So instead of the hand of the person, here you will have a robot catching the part as it comes out of the press and moving it to its final location without dropping it. So you can see here, just clips of the demonstration. It was supposed to work, but yeah, there we are. So you can see that the hand is waiting and the person is doing the pressing, and the robot catches the component here as it comes out and then puts it away without dropping it, so it doesn't get damaged. So that's one demonstration. Here's another demonstration, which I will hope to show you because I think we still have a bit of time. So here's the demonstration where we show you two robots working with a person. Most of the time, the robots work on their own. And then when the robots have difficulties or when there are difficult jobs, then the person comes in to do the work. So here we are. So this is an unscrewing tool. Now, because the location of the turbocharger is not fixed, there will be a need for the robot to search for the screw. And we will show you the searching operation in a few minutes. There we are. You can see it's searching for the screw. Then it finds it. And the person comes in to help, where access is not easy for the robot. Now, this operation is difficult for the robot to perform. This operation is also difficult because of access. And because the robots are collaborative robots, they don't need to be fenced. You can work next to the person, as you can see. So that was our second case study. The third case study is entirely without humans. So here is an automated cell that we are constructing. We have actually completed the cell. And we have 4 robots here rather than 2. And the idea is to use the robots to disassemble a car battery. Now, this is an operation that can be also very dangerous. That's why people are not involved. I'm not showing you the full operation. It takes a long time. So I'll show you only bits of it. We also are constructing a digital twin of it. So here is something that we are constructing. It's not yet finished. The twin is not yet finished. The cell is finished. Yeah. And here is something interesting. You can see the operation, which is to remove this cable. And the robot uses its hand to prise the cable. And then it uses a vision system to look for the cable, and it will grab it. Yes, it's found it, grabs it, and then it pulls it. Then there is one last operation at the end there in order to remove the cable completely. So the robot has to look for the cable. It has found it now. Then it goes and tries to wriggle it. You can see the wriggling operation as well. This is something that we are also studying. Right. So I think, although there is another quick video, I think in the interest of time, I will skip that video. I'll skip this one, if you don't mind, and conclude. So we can see that the first step in remanufacturing is disassembly. And currently, disassembly is very labor intensive. Our project focuses on developing an understanding of disassembly to help robotize disassembly, thus clearing a bottleneck in remanufacturing and enabling smarter remanufacturing. We established this project 5 years ago. We have established a community in this area of robotic disassembly and remanufacturing. You're very, very welcome to join us. There's a lot of work to do. I would say that for a young researcher, they can spend 20 years on this problem of disassembly, and there will still be work to be done. I can tell you that my PhD was on peg hole assembly, and 40 years later, people are still working on the peg hole assembly, not disassembly. So I am sure that in 20 years' time, at least, there will still be people working on disassembly. So you're very, very welcome to join our team to work on this problem and other problems to do with remanufacturing. There is an event, online event organized by our colleague Jun Huang at Wuhan University of Technology in China, and you are very, very welcome to attend. It's a free event. Thank you very much, Samir.
Okay, thank you very much for this nice and informative and rich presentation, opening a new window on robotics, more robotics application. We've got a question asking how is it different remanufacturing and refurbishing? This is more of English, maybe.
Yeah. So refurbishing is really making something look nice. Yeah. So you refurbish your house, you go and paint it, and you repair a little bit of this, a little bit of that. So you refurbish a house. Remanufacturing makes something that is as good as the original. The quality, the functions will be at least as good as the original. If you look at the British standard definition, you will see there is a definition of remanufacturing. Yeah, right. And that is entirely different from just refurbishing.
We've got another question. Does the automation consider it as a clean energy? Because the word trends is to perform zero emission CO2, and robotic needs a source of energy.
Oh, okay. Yes, robots will need energy. So do people. People also need energy. Yeah. So we have not done the analysis of how much robots need compared to people. But what we have done, or not we, but other people have done, is that they have analyzed the benefits of remanufacturing. And as you can see, remanufacturing uses only 10% of the energy required for manufacturing from new.
Right, we've got another question. For difficult access to disassemble, is it considered as another new track for research?
Yes, you could say that you could design the product so that it is accessible for disassembly. You know, you can design a product for assembly, for disassembly. So that is definitely a good research area. Design for disassembly and remanufacture.
That's a genuine idea. So in the future design of new components, we pay attention to disassembly.
And remanufacture.
And the remanufacture, yes.
Yeah.
In a holistic view of the whole process, there is infrastructure, there is cost and time. Do you think, as a holistic view, that is worth going into this direction for the circular economy, and looking at the immense components that we know most of the time they need refurbishing, let's say, or remanufacturing?
You know, if you look at the savings in materials, you save, you know, we don't have unlimited amounts of materials. Yeah. So yes, materials on Earth are limited. And if people use the products and then throw them away, then we waste a lot of materials. So from that point of view alone, it is worth remanufacturing. Remanufacturing doesn't solve all problems, but it can solve quite a few problems for us.
Yeah, another maybe question of interest, do we pay attention to the material integrity in the remanufacturing?
Yes, yes, yes. So inspection, some critical components are inspected internally using X-rays and CT scans and so on. Yes.
Right. We don't have many other questions. So remanufacturing, another maybe question is remanufacturing means also reusing the components in CNC machine tools, of course.
Yes, you know, it can involve reusing components and repairing those that can be repaired and then replacing those that cannot be repaired.
Do you have at the moment, I know that you have started this project a while ago. Do you have anything that is in any sort of production line for specific products?
Yeah, our work is fundamental, fundamental science. So yes, we have not looked at taking the work to industry yet. It's 5 years. The project started 5 years ago.
Right.
Yeah.
All right. I don't think we have questions. So someone is asking how we can register for this event on screen.
Okay, okay. So please write to me, and I will pass your details to Jun Huang. The event is in October, so there's plenty of time.
Okay, so write into Professor Duc, send me an email. I will give you his email address.
Sure. Or I can get Jun to send you the details of the conference and of the workshop, and then you can distribute it to colleagues who are interested.
All right, we can do that, of course.
Yeah,
yes.
yeah.
Right. Maybe another question just coming in now. What are your expectations on the MTBF? This is the mean time between failures and the reliability of remanufactured products.
That's a very good question. And, you know, it is something that people get concerned about, and that prevents some people from using remanufactured product. Exactly. But what I have to say is a remanufactured product according to standard, you know, if it is not done according to standard, then I cannot say anything. But if it is done according to standard, then the quality, the guarantee has to be the same as the guarantee for a new product. That is a product that is remanufactured to standard. So the warranty is the same as for a new product.
There is a say also in maintenance. We say if we do maintenance on time, we are bringing back the component to its initial condition.
Yeah. If you bring it to initial condition, then with the same guarantee, if you can give the same guarantee as for the new product, then it is a remanufactured product.
Right.
So the mean time between failure, the answer is should be the same.
Yes. All right. I don't have any more questions so far. I really thank you very much for the presentation on this new research track on disassembly and remanufacture using robotics or automation. And I hope to see you maybe in the near future. Thank you very much, Professor.
Thank you very much. Nice to see you again.
Thank you. We have, I've tried to summarize what we have seen today. I think there are many national plans to drive manufacturing to high quality for innovative technologies. The industry would like to see working models and easy implementation, not that expensive too as well, and easy to implement. They don't want to waste time. They don't want things to be costly. There are altogether some of the challenges that I think we are up to at the time for the time being, and that opens also clear research tracks at the moment. We have seen that true real time in digital twin is based mainly on control strategy, depending on the use cases. In processes monitoring, finite element is in the heart of digital twin. ANSYS is showing an interest and possibly put in an interface. We'd like to explore this in our center. And that is mainly connectivity between software and hardware and decision making. Human expertise is critically needed to be embedded in an I4.0 system closed loop. Closed loop is extremely important here for decision making embedded in the system, and therefore there is room for research in translating the human expertise into numerical data or digital data. Variety of sensing that need interfacing to be ready for IoT, okay, is also important. Important because we would like to move from the hardware that is heavy, exists today, into an IoT ready to be Internet of Things and wireless communication other than wired communication. Another also room for development. We have just seen now that manufacturing is not about starting from new materials, but also in circular economy, we can remanufacture and reassemble, so that is still economic. And this needs automation of disassembly and reassembly later on. Another new area for robotic applications in manufacturing. I hope that we have learned a lot of things today. I can confirm this for myself, at least. So deep appreciation for all professors from around the world for the nice and rich and full of information today. I would like to thank KICS institution at KFUPM for hosting this technical forum and for the preparation. And I personally hope to meet in person with you professors and in the near future or in the next opportunities that we might have with the Intelligent Manufacturing and Robotics Center at KFUPM. Thank you very much.
Thank you. Goodbye. Goodbye to all.
Thank you. Thank you. Bye-bye.
Sayonara.
Thank you.
Sayonara, yes.